Alright, looks like we are live. Okay, hopefully there is no problem anymore. Let's see how it goes. Let me open the table of content first. Alright. We are on chapter 16, segmentation. Let me open that. Okay, let me reread this first. So far we have been putting the entire address space of each process in memory with the base and bounds register. The operating system can easily relocate process to different parts of physical memory. However, you might have noticed something interesting about this address space of ours. There's a big chunk of free space right in the middle between the stack and heap. Okay, let me open that for reference. Where is it? Figure, this one. Figure 15.2 from chapter 15. There is this allocated but not in use memory, So, yeah, there is a big chunk of free space right in the middle between the stack and the heap. As you can imagine from figure 16.1, although the space between the stack and heap is not being used by the process, it is still taking up physical memory when we relocate the entire address space somewhere in physical memory. Right, it is still taking up physical memory. Okay. Thus, the simple approach of using a base and bounds register pair to virtualize memory is wasteful. It also makes it quite hard to run a program when the entire address space doesn't fit into memory or physical memory, I guess. Thus, base and bounds is not as flexible as we would like, and thus the crux how to support a large address space. How do we support a large address space with potentially a lot of free space between the stack and heap? Okay, do we support a large address space with potentially a lot of free space between the stack and heap? Note that in our example, with tiny pretend address space, the waste doesn't seem too bad. Okay. Yeah, in the example so far, we have a tiny address space, so the waste doesn't seem too bad. But imagine, however, a 32-bit address space, 4 GB in size. A typical program will only use megabytes of memory, but still would demand the entire address space be resident in memory. So in case of the 32-bit address space, if we are still using the base and bound mechanism, we will need 4 GB of memory, even though the actual memory usage is only a few megabytes, something like that. Hello Luigi, what's up? What are you studying today? I am on chapter 16, segmentation here. Basically trying to learn about the virtual memory, Again, the basic concept is that, what is it called? Rather than we are using the memory directly, we use some kind of virtualization and then connect those virtual memory with the physical memory, something like that, if I understand correctly. So previously we learned about base and bound. Where is it? We learned about base and bound mechanism on chapter this one. We are using base and bound mechanism in the chapter 15, but it still has a problem, and that problem is, well, this one. If the address space is large, the base and bound address space will require the entire the entire address space to the entire address space to takes up the memory, For example, if we have 32-bit address space, regardless of how actual memory we use, we will need to reserve 4 GB of memory in size if we are using the base and bound approach here. Basically similar to this figure 15.2, right? We take up some memory for the code and also heap and also stack, but in the middle we have some memory allocated but not in use, So imagine if we only use a few megabytes of memory, but the entire process need to take up 4 GB of memory. That gonna be wasteful, you could say. Like this explanation. The simple approach of using a base and bound register pair to virtualized memory is wasteful, right? Because we have some unused memory too when using base and bound, but it still take up the physical memory space. So there is something like that, and this is the crux of the problem, I guess. How to support a large address space. Right, this is just 32-bit address space. Imagine how big it is for 64-bit address space. Yeah, that's gonna be a lot of wasteful resource, I guess. Maybe something like that. Or maybe the right term is not really wasteful resource, more like unused memory. So something like that. And with that in mind, we learn about segmentation. Now, the generalized space or bounds. Okay, let me read this first. To solve this problem, an idea was born, and it is called segmentation. It is quite an old idea, going at least as far back as the very early 1960. The idea is simple. Instead of having just one base and bounds pair in our MMU, MMU stands for Memory Management Unit, if I remember correctly. Right, this one. Memory Management Unit, basically a specific hardware to manage the memory usage, maybe something like that, at least as far as I understand. So, okay, instead of having just one base and bounds pair in our memory management unit or MMU, why not have a base and bound pair per logical segment of the address space? A segment is just a contiguous portion of the address space of a particular length, and in our canonical address space, we have three logically different segments: code, stack, and heap. What segmentation allows the operating system to do is to place each one of the segments in different parts. Oh. Excuse me. What segmentation allows the operating system to do is to place each one of the segments in different parts. Part of physical memory, and thus avoid filling physical memory with unused virtual address space. And thus avoid filling physical memory with unused virtual address space. Excuse me. Wait a minute. Okay. Let's continue. And thus avoid filling physical memory with unused address space. It's called. So instead taking up the entire, what is it called? Instead using a one contiguous big address space. Hold on a minute. Okay. Instead of using one contiguous address space like this, we spirit that into a segment, I guess. Again, instead of having just one base and bounds for the entire process, why not have a base and bound pair per logical segment of the address space, right? So I'm assuming segment in here, like for example the code segment here, and then the heap segment and stack segment, maybe something like that. I'm still not sure. A segment is just a contiguous portion of the address space of a particular length. Wait, be right back. Okay. A segment is just a contiguous portion of the address space of a particular length, right? Of a particular length, and in our canonical address space we have three logically different segments, like code, stack, and heap, right? I'm assuming this is different segment, right? And then what segmentation allows the operating system to do is to place each one of those segments in different parts of physical memory, and thus avoid filling physical memory with unused virtual address space. Let's look at an example. Assume we want to place the address space from figure 16.1 into physical memory. With a base and bound pair per segment, we can place each segment independently in physical memory. For example, see figure 16.2, page 3. On page 3, there you see a 64 kilobyte physical memory with those three segments in it and 16 kilobyte reserved for the operating system. Again, let me look at figure 16.1 first, an address space again, right? Instead of one contiguous big address space, I guess we can split this into segment. Again, instead of something like this, which means we take up a specific amount of time, amount of memory for each process, and it needs to be contiguous. And what I mean by contiguous is side by side, without any what is it called? Without any missing part, I guess. So we take up the entire space, you could say. But with this one, but with segmentation, we can split this code segment, stack segment, and heap segment into different place independently, not necessarily contiguous in the physical memory, something like that. Okay, as you can see in the diagram, unused memory is allocated space in physical memory, and those large address space with large amount of unused address space, which we sometimes call sparse address space, and those large address space with large amount of unused address space, which we sometimes call sparse address space, can be accommodated. Okay, figure 16.2, placing segment in physical memory, something like this. This is the operating system. Okay, and then this is the stack segment, and this is the code segment, and this is the heap segment. Maybe something like that. Okay, the hardware structure, and again there is no allocated but not in use when using segmentation, right? It is literally not in use, but we are not allocating anything in here. Okay, the hardware structure in our memory management unit, or MMU, required to support segmentation is just what you would expect. In this case, a set of 3 base and bound register pair Okay, the hardware structure in our memory management unit required to support segmentation is just what you would expect. In this case, a set of 3 base and bounds register pair, right? Again, in this case, we have 3 segments, that is code, stack, and heap, something like that. So the MM unit a set of 3 base and bounds register pair. Figure 16.3 below shows the register value for the example above. Each bound register holds the size of a segment. Okay, segment, code, heap, stack, right? Figure 16.3 segment register value. Oh, hold the size of a segment. Okay. 2K, 3K, 2K. Okay. You can see from the figure that the code segment is placed at physical address 32 kilobyte and has a size of 2 kilobyte, and the heap segment is placed at 34 kilobyte and has a size of 30 kilobyte. The size register here is exactly the same as the bound register introduced previously. It tells the hardware exactly how many bytes are valid in this segment. Oh, how many bytes are valid in this segment, and thus enable the hardware to determine when a program has made an illegal access outside of outside of this spawn. Okay. It tells the hardware exactly how many bytes are valid in this segment. Okay. So the hardware can determine when a program has made an illegal access outside of the spawn. Alright. Let's do an example translation. Using the address space in figure 16.1, assume a reference is made to virtual address 100, which is in the code segment as you can see visually in figure 16.1 page 2. When the reference take place, say on an instruction fetch, the hardware will add the base value to the offset into this segment 100 in this case to arrive at the desired physical address, right? So I'm assuming 100 is the virtual address, right? Assume a reference is made to virtual address 100. It is in the code segment as you can see visually in figure 16.1, this one. Oh, where is it? Code segment, okay. The code segment here. Okay. To address 100, and then the hardware will add the base value to the offset into this segment 100 in this case. Okay, so it looks like the virtual address is the offset here, so we add the base with the offset, I guess, to get the physical address, physical memory address, something like that. Okay, to arrive at the desired physical address, right? This one. It will then check that the address is within bounds. 100 is less than 2 kilobyte. Find that it is and issue the reference to physical memory address, this one. Now let's look at an address in the heap. Virtual address for 4200. Again, refer to figure 16.1. This is heap. Yeah, the heap. Okay. This one. Okay. Yeah, I'm still not sure. Oh, where we get the virtual address? Is this the virtual address? Yeah. Well, let's just assume it is. virtual address 4200 here. If we just add the virtual address 4200 to the base of the heap, okay, the base of the heap, 34 kilobyte here, right? We got the physical address of this one, 39,016, which is not the correct physical address. What we need to first do is extract the offset into the heap. Okay, that is which byte in this segment the address refer to, because the heap start at virtual address 4 kilobyte. Okay, the offset of 4200 is actually 4200 minus 4096 or 104. We then take this offset 104 and add it to the base register physical address 34 kilobyte here. The base is 34 kilobyte. Okay, okay. To get the desired result 34,920, the physical address space. Okay. So what is it called? We are not directly adding the offset here, because we start the virtual address space not from 0 but from 4 KB, I guess, something like this. So we need to subtract the actual address, the virtual address space, with the base of virtual address. I assume something like that. Can we start the heap start at virtual address 4 kilobyte or KB here? So the offset is not exactly 4200, but it is 4200 minus 4096 here. So the virtual address minus the base address. The base virtual address, maybe something like that. And then we take that offset after this calculation with the base register physical address. So we get the physical address for the heap, something like that. What if we try to refer to an illegal address that is a virtual address of 7 kilobyte or greater? 7 kilobyte or greater, something like this, right? The heap is only until 7 kilobyte, I guess, maybe something like that. So what if we try to refer to an illegal address that is a visual address of 7 kilobyte or greater, which is beyond the end of the heap? You can imagine what will happen. The hardware detects that the address is out of bounds. The address is out of bounds, trapped into the operating system likely leading to the termination of the offending process. And now you know the origin of the famous term that all C programmers learn to dread, the segmentation violation or segmentation fault, for short called segfault. The segmentation fault, okay? Segfault. Alright. So we also keep track of that, okay? Keep track of the size of the segment, I guess. Or the size of the segment. Maybe. Alright. Okay. Yeah, from this example, we learned that the address space is not what is it called? Is not start from 0, so we cannot add directly that as is. It is kind of different from the code segment here, because the code segment start from 0, right? We can add that directly, but for the heap in this example, we cannot do that, and we need to do some kind of calculation, I guess. The virtual address space minus the base virtual address space. So with this segmentation we have, I guess, the base physical address and the base virtual address. Maybe something like that. Base virtual address and then base physical address. Just something to keep in mind. And then when we try to access illegal address that is not allocated, right? Even though we are already doing this calculation, the virtual address minus the base virtual address, we will still get the illegal physical address space, and the hardware detects that, and then will likely leading to the termination of the offending process, something like that. Usually called segmentation fault, or some people call that segmentation violation, I guess. But the one that I see a lot is segmentation fault. Okay, let's continue. Which segment are we referring to? The hardware use segment register during translation. How does it know the offset into a segment and to which segment an address refer, right? How does it know the offset into a segment and to which segment an address refer? One common approach, sometimes referred to as An explicit approach is to chop up the address space into segments based on the top few bits of the virtual address. Sometimes referred to as an explicit approach is to chop up the address space into segments based on the top few bits of the virtual address. This technique was used in the VAX or VMS system. In our example above, we have 3 segments, thus we need 2 bits to accomplish our task. If we use the top 2 bits of our 14-bit virtual address to select the segment, our virtual address looks like this. Segment offset. Wait a minute. If we use the top 2 bits of our 14-bit virtual address, select the segment, our virtual address looks like this. Wait, I'm kind of curious here. Do we also, what is it called? Do we also chopping up the virtual address space? I assume yes. Maybe. Yeah, so we are chopping up the virtual address space here into different segments, right? Segment register value. We have 3 segments, thus we need 2 bits to accomplish our task. Why we need 2 bits to accomplish our task when we have 3 segments? I'm still not sure about that. Wait, let me read the aside first, I guess. The segmentation fault. The term segmentation fault or violation arises from a memory access on a segmented machine to an illegal address. Humorously, the term persists even on machines with no support for segmentation at all, or not so humorously if you can figure out why your code keeps faulting. Yeah, not so humorously. Okay. If we use the top 2 bits of our 14-bit virtual address to select the segment, our virtual address look like this. Yeah, my question is that why we need 2 bits to accomplish our task? We need 2 bits our task when we have 3 segments. How do we go into this assumption, I guess? or conclusion maybe. Should I read this? Let me try to read again. One common approach, sometimes referred to as an explicit approach, is to chop up the address space into segment based on the top few bits of the virtual address. Okay, on the top few bits of the virtual address. Okay. In our example above, we have three segments. Thus, we need 2 bits to accomplish our task. If we use the top 2 bits of our 14-bit virtual address to select segment, our virtual address looks like this. Of our 14-bit virtual address to select the segment, virtual address look like this. This is the offset. This is the segment. Does it note the offset into a segment? Right. And 2 with segment and a deceiver. Okay. In our example, then if the top 2 bits are 0, 0, the hardware knows the virtual address is in the code segment and thus use the code base and bound pair to relocate the address to the correct physical location. If the top 2 bits are 0, 1, the hardware knows the address is in the heap. Oh. The hardware knows the address is in the heap, and thus use the heap base and bound. Do we use the 2 bits because, well, it is more than 2 segments, If we only use 1 bit, right, instead of 2 bit, we can only use 0 and 1. But because we have more than 2 segments, using only 1 bit is too few to accomplish our task, because again it only has 0 and 1. So we need 2 bits so that we can what is it called? We can distinguish between segments, something like that. So this is the question. The answer may be something because when we only use 1 bit, we can only represent 2 segments, that is 0 and 1, but with 2 bits can represent more than 2 segments. I'm assuming 4 segments, I guess. Segment, that is 0, 0, 0, 1, 1, 0, and 1, 1. something like this. That's why we need to pitch to represent 3 segments. Yeah, maybe something like this. Maybe. Again, I'm still creating the hypothesis, I guess, which can be wrong. But from the explanation here, right? If the top two bits are 0, 0, the hardware knows the virtual address is in the code segment and thus use the code base and bounce pair to relocate the address to the correct physical location. If the top two bits are 0, 1, the hardware knows the address is in the heap and thus use the heap base and bound. Let's take our example heap virtual address from above with the virtual address 4200 here and translate it just to make sure this is clear. The virtual address 4200 in binary form can be seen here. Okay, interesting. Okay, this is the segment 0 and 1 and the rest is the offset. In a 14-bit, what is it called? Virtual address. 14-bit virtual address. Okay. Yeah, it is 14, right? 14-bit. As you can see from the picture, the top two bits 0 and 1 tell the hardware which segment we are referring to. The bottom 12 bits are the offset into the segment, this one, or hex, yeah, 0x068, I guess. Oh, or 104 in decimal. Interesting, let me check. Hex to decimal. Oh, interesting. Okay. Alright. Thus the hardware simply takes the first 2 bits to determine which segment register to use and then take the next 12 bits as the offset into the segment. By adding the base register to the offset, the hardware arrives at the final physical address. Note the offset is the bounce check tool. We can simply check if the offset is less than the bounce. Note the offset is the bounce check tool. We can simply check if the offset is less than the bounce. What is it called? The limit size, I guess. From this one, for example, the size, the bound size or the limit size. Check if the offset is less than the bounds. If not, the address is illegal. Thus, if base and bounds were arrays with one entry per segment, the hardware would be doing something like this to obtain the desired physical address. Get top 2 bits of 14-bit virtual address. Okay. We use, what is it called? Sexive. We use bitwise operation, I guess. Shifting the bit, maybe something like that. Now get offset. Okay, yeah, we are using bitwise operation here. If offset more than or equal bounds, raise exception, protection fault, else, right? Physical address, access memory. This kind of similar from the simulation on chapter 15 here. The, what is it called? The relocation.py. You can take a look at this if you want. There's a similar condition, something like this. Yeah, the interesting part is if it is equal to the bound. Alright, maybe we start from the 0 2. So it should be bound -1 as the last address, I guess, or offset, maybe something like that. In our running example, we can fill in values for the constant above. Specifically, segmax would be set to this one, sexive to 12, and offset max to this value. You may also have noticed that when we use the top 2 bits and we only have 3 segments called heap stack, one segment of the address space goes unused. One segment of the address space goes unused. To fully utilize the virtual address space and avoid unused segment, some system put code in the same segment as the heap. And thus use only one bit to select which segment to use. Okay, right. So I'm assuming one segment of the address space go unused. I'm assuming the one that might not be used is the heap here. We might not allocate any heap memory, right? Maybe something like that. To fully utilize the virtual address space and avoid unused segment, some system put code in the same segment as the heap and thus use only one bit to select which segment to use. Right, again, similar to my previous explanation. If we only use one bit, we can only, what is it called? we can only represent two segments, that is 1 and 0. 0 and 1, maybe something like that. But with 2 bits we can represent up to 4 segments, I guess. That is 0 0 0 1 1 0 and 1 1. That's why we need 2 bits to represent the segment. So some system here put the code in the segment as the heap and use only 1 bit to select which segment to use. Another issue with using the top so many bits to select a segment is that it limits use of the virtual address space. Specifically, each segment is limited to a maximum size, which in our example is 4 kilobyte. Using the top 2 bits to choose segment implies the 16 kilobyte address space get chopped into 4 pieces, or 4 kilobyte in this example. Okay, using the top 2 bits to choose segment implies the 16 kilobyte address space get chopped into 4 pieces, or 4 kilobyte in this example. If a running program wishes to grow a segment, say the heap or the stack, beyond that maximum 4 kilobyte, the program is out of luck. There are other ways for the hardware to determine which segment a particular address is in. In the implicit approach, the hardware determines the segment by noticing how the address was formed. There are other ways for the hardware to determine which segment a particular address is in. In the implicit approach, the hardware determines the segment by noticing how the address was formed. Oh, interesting. How the address was formed. If, for example, the address was generated from the program counter, that is, it was an instruction fetch, then the address is within the code segment. If the address is based off the stack or base pointer, it must be in the stack segment. Any other address must be in the heap. Okay, interesting. Generated from the counter, from the program counter, and then base of the stack or base pointer. I'm still not sure how we notice if the address base of the stack, generated from the program counter. I can kind of imagine that like from the instruction fetch, maybe we will get what is it called, a unique kind of address from the program counter here, maybe something like that, but based off of the stack. Do we also have a unique kind of address when using the address from the stack? Maybe and then only other address must be in the heap. Okay, so that is the implicit approach. There's explicit approach and implicit approach. Alright, what about the stack? Okay, there's support for sharing too. Fine grain versus coarse grain segmentation. Okay. Alright. I think we will continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.